All right. Hello, everybody. So my name is Damith-A. I am a first-year master's student at York University, all the way from Toronto, Canada. And today I'll be presenting our research in the development of a mixed reality teleoperated robot arm that uses stereo vision and hand tracking for construction applications. So the agenda for today's keynote, I'll begin by presenting some background information about our research topic. And then I'll move on to our research aim, followed by our objectives and methodology. And then I'll briefly present some preliminary results we have, and then I'll finish off with some timeline and some future work and things that we're working on. So for our research topic, we were focused on the architecture, engineering, and construction sector, specifically the construction industry. Right? This is one of the most beneficial industries to society. It's responsible for developing homes, buildings, factories. But what we notice is that it performs at a very high cost, right? One of the major flaws of the conventional construction site is its high volume of safety hazards for its on-site workers. And some of these reasons include workers being exposed to high concentrations of particulate matter, collisions with heavy machinery, and falls off of unsecured high-altitude sites. What we notice is a working solution to these types of problems in other industries is the application of automation and robotics into performing these hazardous and strenuous tasks. Right? The automotive industry is a great example of this, where they've deployed robotic manipulators to assemble vehicles with great precision and accuracy. And likewise, we see the advent of robotics and their precision in the medical sector with these surgical robotics, and then in the agricultural fields as well with crop management robots. And all this to say the integration of robotics not only improves task efficiency, but product quality and just overall worker safety. Now, despite these many benefits, there's actually a lack of automation and robotics applied in the construction industry, and the primary cause of this is the highly unstructured and dynamic environment that is a construction site, right? So generally, robotics are applied in two main ways. One, by pre-programming robots to perform very specific tasks in a very controlled setting. And two, more recently, using machine learning techniques such as deep learning and reinforcement learning to train robots to perform these very strenuous tasks. But the problem with these two types of solutions is that the pre-programmed robots, they have a very difficult time adapting to changing tasks, and there's also a lack of quality available training data for construction applications specifically. So rather, a more emerging solution to this challenge is the concept of human-robot collaboration, or HRC. So this is where humans and robots collaboratively work together to complete tasks, and an extension of this is human-robot interaction. This is where intuitive interfaces are designed that enable us to take advantages that robots provide, such as their precision, their strength, their deployability, while still maintaining that human component, the experience, the creativity, and the decision-making skills of human operators. And this is really where our research is focused on. It's how can we develop an intuitive human-robot interaction interface that enables operators to complete these hazardous and strenuous tasks from a safe environment through leveraging these robotic solutions. Now, it turns out that there are three key challenges that arise when trying to deploy an effective HRI system. The first is being able to develop provide accurate depth awareness of the robot's workspace. The second is being able to develop an intuitive control interface for teleoperation. And the third is being able to provide those operators with a high level of situational awareness for just overall worker safety. So to tackle these challenges, we propose utilizing spatial computing technology such as VR headsets and coupling that with stereo camera systems that replicate human-like vision and using hand tracking algorithms to develop an intuitive mixed reality teleoperation interface. And this brings me to our development process. So to begin, what is mixed reality? Well, mixed reality is the combination of both augmented and virtual reality. In virtual reality, users are fully immersed into a digital environment, while in augmented reality, there are digital components that are overlaid onto the physical world. And mixed reality sort of combines aspects of both, where digital and physical objects can interact with each other in real time. And to achieve this type of immersion, head-mounted displays are used. So these have a left and right display, each with a lens which enable the perception of human-like vision through the generated stereoscopic images. And for our application specifically, we're making use of the Meta Quest 2 VR HMDs. The other very key technology to this application is stereo vision. So stereo camera systems are traditionally used for point cloud reconstruction through the extraction of depth information. How they work is they have these two cameras that are separated by a fixed known distance that render slightly two different views of the target scene. And then the disparity between these two images can be used to extract that missing depth information layer using triangulation techniques. So for our application, we're using the Z Mini stereo camera that's developed by Stereolabs. And what's really neat about this camera system is that it supports mixed reality development. And you'll see some examples of this later on, but what I really want to highlight here is this integration between VR headsets with stereo vision systems is not something that's all that new. In the past, it's actually shown to increase user performance, depth cues, and usability in the field of mobile robotics when it comes to teleoperation. So the system that we've developed consists of taking a high degree of freedom robotic arm and attaching this stereo camera system into these hazardous environments, right? The key idea is that these stereo images are streamed in real time to the VR headset to create this mixed reality interface. And in this interface, the operator is able to visualize the robot's workspace with human-like vision, which is far more immersive than any other systems that are currently being used. And then we perform real-time hand tracking to provide an intuitive control input system. The first step here, so we began by simulating this system because we wanted to show if it indeed increases task efficiency and just overall worker safety. We used the Unity engine to simulate a 4-axis industrial-grade robot arm along with that stereo camera system. And the first step was developing a real-time inverse kinematic solver for robot arm motion planning. So robot arms generally consist of a set of links, each connected by a joint that has a fixed degree of freedom. And inverse kinematics refers to determining the necessary joint angles so that robot arm can reach a certain target in 3D space. So this is actually a video of one of our first simulations we did for real-time target tracking. In the scene, you can see there's a 4-axis robot arm and a 3D coordinate is passed as input to the system, and it computes an inverse kinematic solution every iteration to return a new array of joint angles to be able to track that target in real time. So with this, we can now move that robot arm to any point in its workspace. So after this, we moved on to simulating that stereo camera system. So here, we've attached that Z Mini camera to the end effector of the robot arm. And this allows the operator to have a first-person view of what the robot sees. But as I mentioned in the beginning of this presentation, the one challenge about being able to deploy an effective HRA system is being able to provide the operator with a high level of situational awareness. And this is quite challenging to achieve when you have a fixed camera view. So to solve this problem, we took that camera system and we mounted it to a 2-axis servo-actuated gimbal. So as the operator moves their head around, the pitch and the yaw angles of the HMD are tracked and then remapped to each of the 2 servo motors. And this allows that camera system to mimic the head movements of the operator. So they can look around the environment as if they were there in real life. The last component is developing intuitive control input system. So conventionally, robot arms are teleoperated using keyboard controllers. But what we find is that this is very limiting, very slow, and very unintuitive. So we decided to use a control input system that we're all familiar with, our hands. Right? So the VR headset has 4 built-in cameras that are used for spatial mapping. There's great library plugins in Unity that take advantage of this, perform computer vision techniques to perform real-time hand tracking. And using this, we can track the joints of the operator in real time and spatially map them into the VR scene. Right, so just to recap up to this point, we can move the robot arm to any point in its workspace. We can visualize its workspace very effectively. And now we have a very intuitive control input system. And the last step was sort of putting this all together to develop an intuitive control interface. So This is our first iteration of the mixed reality HRI system. You can provide omnidirectional control to the arm by simply pointing in where you want the robot arm to move towards, and it will move towards that direction. And because we can do these little gesture recognitions because of the joint rendering, we can do little things like pinching to close the gripper to pick up bricks and then stack them in various locations. So what we found during these simulations was that this system was not only not only was it good at completing tasks, but it's also much more intuitive when it comes to robot teleoperation. So after we validated the system in a simulation environment, we moved on to developing a real-world implementation because simulation can only show you so much. So for this, we're using a 6-axis collaborative robot arm. Some specifications about this arm: it is highly programmable in various environments, including ROS, which is the Robot Operating System. And I just want to touch on what ROS is because it's a very important piece of software, not just for our application, but for robotics in general. This is an open source meta operating system that's primarily used to develop robot software, and it operates under the data distribution server architecture. And it's really important because it allows us to interface with multiple sensors and components in real time. Things like LiDAR sensors, cameras, robotic arms, and this is sort of the standard for research and industrial applications when it comes to robotics. And once again, it's what majority of our system is built upon. So the physical implementation has 3 key segments. There's a user input segment, which is really that mixed reality interface. There is a middleware segment, which is on a single board computer that does data processing. And then there is the robot arm segment itself. And this is a look at the first iteration of that physical implementation. So you can see the operator wearing the headset on the top left video, just pointing where they want the arm to move towards. And then you can see what the operator sees on the top right video, which is what's seen on the VR headset. You can see the robot action's global movements in the bottom left video, and then we've also been able to track the movements of the robot arms and then plot it in real time, which you can see in the bottom right. And what's important is we've been able to go from simulation to real-world implementation pretty quickly. And what I really like about this system is how intuitive it is to control this robot arm. So this is one of my favorite videos where we've taken that pinch gesture and made it into a variable prismatic gripper controller. So you can pinch your finger variably to control the end effector. And this allows the operator to pick and place different objects very easily in the robot's workspace. So once we had this physical implementation done for the first iteration, we wanted to see how well it stood up to existing teleoperation interfaces. So we compared it to the 2 most common ones. The first one is a computer video keyboard teleoperation. This is simply where a video feedback of the robot is displayed on a 2D computer, and then a keyboard is used to teleoperate that robot arm. And the second one is a line-of-sight keyboard teleoperation. This is similar to the first one, except the operator standing next to the robot arm and using the keyboard to teleoperate it. The experiment was quite straightforward. The robot starts at a fixed position, and the goal is to drive the robot arm to this target cube using the different teleoperation methods. And we've been able to measure the trajectory of the robot arm as well as how long it took to complete that task. And we have some preliminary results that I'd like to share with you. So the 2 graphs that you see on the far left are the trajectories of the robot arms when using the conventional teleoperation methods. And the graph on the far right is when using the mixed reality teleoperation system. And you can just tell through inspection that the conventional methods are very jagged and inconsistent, whereas the mixed reality system is almost a straight line from start to finish. And we can attribute this to the increased depth cues of the stereo camera system and that mixed reality view. We also have the distance minimization graph. So how long did it take to complete these tasks? So the mixed reality system, which you can see highlighted in red, was not only faster, but also more consistent at completing the task than any of the other conventional teleoperation methods. And just to put these into perspective, so the mixed reality system is almost 28% faster than the conventional line-of-sight keyboard teleoperation system and almost 40% faster than the computer video keyboard teleoperation system. Now, I must say these are very preliminary results and we need to do many more experiments, but these are nonetheless positive results. And from here, we go on to various ways we can apply this into construction tasks. So we're going to go all the way back to the simulation component. Here we've given the operator the task of stacking those set of bricks, but this time they're asked to stack it in a very specific format. And because we have this mixed reality view, we can superimpose 3D models into the robot's interface, and that constantly gives the operator this as built versus as design comparison for them to design various structures. So this is just using that hand tracking system to build this pyramid structure. And we moved on to sort of trying to do this in real life as well. It's quite difficult to do with real world systems, but this is where the robot arm is asked to place a block on top of the other, and we spatially mapped this 3D cube to help the operator understand exactly where to put that block. So it moves forward, they drop it, and then they move back. And to achieve this, we're using Aruco targets and OpenCV libraries to get pose estimations of those targets, and then we spatially map various objects into the robot's workspace. And we want to sort of take this to the next level, so getting away from just stacking cubes to building more complicated structures, such as these complex pyramid shapes. We're also working on an end effector tool that helps the robot arm drill and screw things in. So having these sorts of diagrams helps. And then some of the things we want to achieve later is doing things like framing for building construction. Which brings me to my last set of slides. So by the end of this project, we want to streamline building information modeling data into our Unity system and spatially map them into the VR scene so that they have a variety of models to work with. And then we also want to improve our robot arm control interface. So right now we can only provide omnidirectional control, but we want to be able to provide roll, pitch, and yaw controls using hand gesture algorithms so that we can provide more complex manipulation tasks to the operator. So I just want to take a second to acknowledge the funding from NSERC for helping making this project happen, and also the continued support through the Lassonde School of Engineering and York University for helping me work on this project, as well as my supervisors and my lab mates. So with that, thank you, and I'll take questions.